All right, so we can go ahead and get started. So my name is Subramanian Ramaswamy. I'm a program manager in the .NET Common Language Runtime team, which is essentially the kernel of the .NET framework. And since pretty much only my mother can pronounce my name correctly, I also go by a shorter name, Mani. I'm going to be talking about .NET functionality and performance improvements that we have made in .NET for Windows Phone 8. So even though my name and the title indicates that I get paid by the letter, I assure you it's not so. If it were, I would make it longer. So before I start, I want to thank all of you for coming to the Build conference. I hope it has been super exciting and useful for all of you. And we folks at Microsoft have been pretty amped up about it. So with that, I'll dig right in. So I assume most people here are familiar with what the CLR is. You must have had to do something with .NET development if you show up at this talk. But still, the CLR is basically a short form for the Common Language Runtime, which is essentially the execution environment for all managed code. It provides you, with an automatic memory management system, which automatically takes care of allocation and deletion of objects. It provides you with exception handling, security model, lots of features, and also provides you with a core set of base class libraries. So on top of this, sit the frameworks which make .NET development so productive. For particular interest to this crowd, with respect to Windows Phone, would be the Silverlight for Windows Phone framework, which I've shaded in red here. So yes, that's all fine, but your question would be, wasn't Windows Phone using NetCF? For folks who don't know what NetCF is, NetCF stands for the .NET Compact Framework, which is essentially a pared-down version of the framework targeted towards resource-constrained embedded devices. So coming back to the question, wasn't Windows Phone using NetCF? Yes, it was, before Windows Phone 8. With Windows Phone 8, we've actually, now .NET for Windows Phone 8 now actually uses the same engine that powers Silverlight web apps across millions of browsers worldwide. It's also known as Core CLR. And as you will see through this talk, this opens up a lot of powerful productivity features and performance features to .NET developers. Next, so what have we been up to for Windows Phone 8? So I don't know how many of you hail from Seattle, but the weather that you saw over the last few days is pretty par for the course here. It's pretty much always raining here. Well, for some reason, this summer we had a lot of sun. It's pretty unusual for our region. So, and folks here are actually quite afraid of the sun. So instead of going out and enjoying the sunshine, we actually hunkered down in our offices and wrote some features for Windows Phone 8. So what are the, I kind of split my talk into two sections based on what we are providing for Windows Phone 8. We're providing great functionality features that makes .NET development ever more productive. And obviously, that has to be queued up with performance wins, because ultimately, the customers need to have a great experience. And the less time that you spend fiddling with your code, the more productive you are. So what are some of the functionality features that I'm going to call out during this talk? So we now support native game engines. So this was an ask for a lot of developers that we have some code that was sitting in C or C++. We don't want to pay the cost for migrating it over. Can you please allow us to write hybrid apps? So we have the support for that now. Now, with the mushrooming of platforms, if I take one slice, you have Xbox, Windows Phone 8, Windows 8. Developers are now, having to target multiple platforms and having to maintain some version of source code per platform. We'll see how .NET for Windows Phone 8 gives you more efficient means of targeting multiple platforms simultaneously. Finally, you need to write fluid and responsive apps, especially in today's App Store world. If somebody actually downloads your app and the GUI is not as smooth or buttery as it needs to be, you're going to be rated low. So we see with the async and await model that we've exposed in .NET for Windows Phone 8, it helps you write fluid and responsive apps. Now I come to the performance features that we've added in .NET for Windows Phone 8. We actually pretty much went whole hog on performance. We invested a lot into this. One of the key features that we added was something called compiler in the cloud that helps improve app startup times dramatically. Dramatically, not just for Windows Phone 8 apps on Windows Phone 8 devices, but also for Windows Phone 7 apps on Windows Phone 8 devices. And the beautiful thing about this is pretty much it has no developer impact. You still continue with the IL development model that you love. And customers, it's entirely transparent to customers. All they're going to see is apps start faster. We also improved the app execution time and responsiveness. So your apps can run faster, will have better memory profiles, because we have an improved code generator and garbage collector. So our code generator generates more optimized code than it did in NetCF. And the GC is much more fine-tuned, or is self-tuning, so to speak. So I'll go into a little bit of detail in all of this, and some of this I'll go into a lot more detail, especially the compiler and the cloud one. All right, so this was one of the key asks, like how do we actually write hybrid apps? How can we write hybrid apps? Because one of the main pain points for developers is, you had some C or C++ code that was written 10 years ago maybe, and which has been hand optimized to heck and beyond. You don't want to pay the cost of actually porting it over, making sure you're doing the same optimization so it actually performs fast. Or maybe it's the case that you just want to borrow a library from somewhere and just use it with your app. We could have gone a couple of ways here. We could have said, use pinvoke and deal with marshalling and kind of leave you on your own to do everything. But what we did here is we provided you a very seamless integrated solution. So basically, what we provide you is, for example, if you have some native code foo, and if you want to use it from your managed code, all what you got to do is to write an interface, write a WinRT component, and create an interface, say foo WinRT interface. That's pretty much all what you have to do. Now, the foo WinRT interface, it's something that's directly accessible from your managed code. Just like any other managed code, you get IntelliSense, all that jazz for free. And I'll be showing you a demo of this, which makes it very clear how easy and transparent it is. And again, performance has been one of our key focus areas. So not only did we actually provide you with a seamless experience for writing hybrid apps, we made sure that the intra-boundary performance has been optimized. So every time you actually call a native code, you don't pay a huge penalty. Basically, we make sure that that path has been optimized. So a kind of a similar question is, sometimes we just need to access native APIs. We need to access Windows APIs. So what can we do? Again, here, we had a couple of choices. One choice is we could have exposed the Win32 APIs, have you access them via pinvoke, and again deal with marshalling and all that jazz again. Another option that we could have done is we could have wrapped these APIs around .NET class libraries, basically created new class libraries that expose those APIs to you. Now, the problem with the latter approach is we would always be playing catch-up. So every time there is a new API added, we need to make sure that we add a corresponding API that is exposed to .NET developers. So instead of that, what we did is we basically exposed those WinRT APIs directly to you, the modern APIs directly to you. So you can pretty much access them as you would any type in the .NET class libraries. It's seamless. It's straightforward. And the thing is, you don't even know that you're writing a hybrid app, because when you call a Win32 API or WinRT API, it's in effect a hybrid app. You're calling into native code. But for all purposes, you will actually just see that it's just like writing a managed code. We take care of the interop automatically for you. So this story is very similar to what we have done in Windows 8 as well. So to that extent, it brings the stories closer together. So now let me show you a demo of what I mean by this. And so I'm going to show you a demo of a Go application. Just going to show you the source code for now. So we basically wrote a Go application, which is kind of similar to a checkers game, I guess. And we had a GNU Go library that's there for a few years, I guess, and I believe some iOS apps are also using it. So we just have a GNU Go library, and it has a bunch of methods in it that we want to access. So what we do is, once I get my mouse cursor back, so we create something called a WinRT component. So in this case, we create a WinRT interface. So if I look at the header file, which I have opened here, so I'm basically importing a bunch of methods from the native library that I want to use. And I've just created an interface. And if I go into the implementation of the interfaces, I'm just calling the same methods that I just imported. So that's pretty much all what I did. Now, let's see how I can use this. Now, this is all straightforward. Now, say, for example, AI move was one of the interfaces that I created. Calling it is just as straightforward as calling any other managed object. So it's right there. So it's very straightforward, and you get IntelliSense again. Everything is there just for free. So in a sense that you don't even know that, unless you actually, you don't even have to know about the interactions with native code and everything. All what you need to do is to create an interface that wraps it, and you're done. Boom. Similarly, now if you were writing your own C++ code, all what you do is, you don't have the native library that you're using. Your implementation goes into the interface implementation, and that's it again. You're done. So what this does, and again, as I mentioned earlier, we have made sure that the interrupt boundaries are well optimized. So again, you will see very good performance with this. This is a fascinating interrupt story. Seamless, integrated, just like you're writing managed code. And in fact, that's what you're doing. So now I'll move on to the next part of the talk. Welcome. Which is portable libraries. Now, I mentioned briefly at the introduction that there is a problem for developers, the mushrooming of platforms. So if you, for example, I picked on Xbox, Windows Phone 8, and Windows Phone. Now, if I actually opened a project in Visual Studio, can you guess the number of options that we have? There are about 20 options here. So basically, if you were doing this manually, you probably will have 20 different source files, or 20 different project files, actually, with different changes in sources, and that's what you'll have to manage. Well, the good news about maintaining 20 different versions of your sources, you probably will know your code better than you know yourself. The bad news is you probably know your code better than you know yourself. So once again, as a .NET developer, you're actually well placed here. So we've kind of made this problem, we kind of help you tackle this problem more efficiently. So the way we do it is by introducing something called portable class libraries. So one thing that we could have done is we could have done something that minimizes your source problem. That is, okay, instead of maintaining 20 different versions of your source, you just have to maintain one version of your source that you can use across multiple frameworks or platforms. But we went one step ahead. We didn't stop at the source boundary. We said, well, if you have one version of your source, might as well allow you to actually copy one binary everywhere. And that's what we actually did. So you can compile down your source to a binary, and you can use it across multiple platforms. And the advantage with compiling it down to a binary is that now you can run your test against the binary, make sure everything works. It's all hunky-dory. So this is how you add a portable class library. As you can see, you can select which are the platforms you want to target. And basically, that makes sure that whatever code you're writing is portable across these platforms. So the only part that you will have to write is the different XAML for the different platforms. The engines are common. You just have to maintain one version of your source. You compile it down to one binary, and that's the same engine that you can use across platforms. So my colleague called Daniel Kleistad is basically having a talk at 12:45 in the Nexus Normandy room. So he will be giving you a much more hands-on talk on how you can actually use portable libraries, and he will talk about the model view model pattern to create cross-platform apps. Now, moving on to the next step. So, in today's world, you need to write fluid and responsive apps. As I said, if your apps aren't responsive, people aren't going to buy your apps. So if you're doing some heavy processing on your GUI thread, for example, you're doing some HTTP request, and you're waiting on it on your GUI thread, people are not going to be very happy. Kind of an extreme case is, let's look at Outlook. If Outlook was synchronous, it wouldn't allow you to read or write emails when you're sending and receiving, when you're connected to the Exchange server. That wouldn't be a great customer experience. Now, the problem here is synchronous programming is easy, well understood, cheap. Everyone knows how it flows, easy to debug, easy to write. Asynchronous programming is traditionally difficult. you got to deal with creating background worker threads, make sure you have the event handlers plugged in, make sure you write a whole lot of glue code to make it all stick together, make sure you test it, debug it. There'll be bugs there. It's messy. It's not straightforward. So we kind of have a choice here. Like, apps need to be either responsive, in which case you have to write using the background worker threads and all that stuff, or you write synchronous versions which are not going to satisfy your customer. Well, for Windows Phone 8, for .NET for Windows Phone 8, we have actually provided something called async and await, which basically makes your app a lot more responsive without making your programming any complex. So a very simple, dumb example is, if you have a synchronous method that does some work, and it depends on get work, which is, say, for example, something that relies on hitting the internet or doing some long latency operation. This is how it looks. Now, the problem is, it cannot proceed. Do work, you cannot really spawn off multiple requests simultaneously, even though you know that it's all going to be long latency. So you're basically adding up the latencies. Now, in the async model, it's very straightforward. All what you do is you create a task, and you basically await on that task. So async automatically takes care of resuming from the point it needed to. So no event handlers, nothing, anything. So in this case, what will happen is when you invoke getWorks tasks, it's actually going to send out those requests. And whenever those requests come back in, it will proceed executing the doWork method. So basically, what it does, it allows you to actually make sure that your GUI thread is not frozen because you're sending some HTTP request and the like. So we have actually provided a lot of async versions of the APIs. So in order to make your apps more responsive, I recommend you go ahead and use those async APIs everywhere you can, so you're not hogging up the GUI thread. So now I'll show you a demo of what I mean by this. So this is essentially, I'm going back to the Go application. So I just have written a bunch of code, and initially I just wrote synchronous code, which basically does, gets what the AI move is, and then refreshes the board to make sure it's happened. So if I play this game, let's start up the app. I had already deployed it, and that's why I didn't have to rebuild this time. Let's start a new AI game. So I'm just going to start playing. I'm not very good, as you might, if you are a Go, if you know what the game Go is, you probably know that already. I'm just going to be randomly making moves. So the key here is, every time that I make a move, you can see that I made my move, and the AI is actually processing, but the GUI is still frozen up. And the more I play, the more the AI has to think, and the longer it takes for the GUI to actually come back. So for example, at this point, when I actually keep a button there and I press submit, it's still showing black's move. Well, black's move is actually done. It's white's move. It's thinking about white's move. So let's see how we can make this better. So this is what we have today. Do AI move synchronous is what I call, and that's all what it does. Now, in the earlier days, if you wanted to do something with this, you probably have to create something like, you have to create a background worker thread, you have to write all that jazz, and then you have to hook up event handlers to it, and then, as I said, you have to debug it. It's very likely that you got it wrong on the first try. You got to go back, fix bugs, a whole lot of pain. Now, in the async world, life is a lot simpler. So what I did is I just wrapped AI move around a task.run delegate, and I just await on it, and that's pretty much all I do. And then instead of calling do AI move synchronous, let me just call do AI move asynchronous and make this method async. Now I'll build and So it's still deploying. Deploy in a minute. So I'll start this the same kind of game. I'm not changing any game settings. So this time you'll actually see that you actually saw the white smoke flash up on the device. So for example, when I'm submitting, after I submitted, the white smooth actually shows up. So whenever the AI is actually thinking, the GUI is not frozen up. So when I'm done submitting, whenever the AI engine is thinking, you can actually see the GUI getting refreshed. See that? So that's pretty much what I wanted to show you. So the async development model is simple. It makes it a lot easier to write asynchronous apps without dealing with background worker threads and everything. So anything that you can actually run asynchronously, web requests are common. If you're reading off the disk some files, streams, and stuff like that, that's another common area where you could actually use async. And we provided a ton of these async APIs as well. So you can write very fluid and responsive apps using .NET for Windows Phone 8. So now I'm going to go into the next segment of my talk, which is performance. And I'm going to do a little more deeper into some of these items. So app startup. Well, we all know startup is a problem. It's always a problem. People are never satisfied with how fast apps start. So in .NET for Windows Phone 8, we actually invested heavily in improving app startup via the compiler in the cloud. There were a lot of features that contributed, XAML to binary translation being one, but compiler in the cloud was one of the biggest features that we invested in. Also, you'll actually find that this has little development impact, and it's all transparent to the customers. Plus, Windows Phone 7 apps that run on Windows Phone 8 devices get this for free, get the benefits for free. So let's dig a little more deeper on what this all means. So firstly, let me show you what the performance that we are actually getting. So Windows Phone 8 devices are about 2 times faster than Windows Phone 7. A lot of it was because of the compiler in the cloud investments. It was a pretty significant win, and we added a lot more features on top of it as well. So firstly, some background. So how does actually machine code run? So your phone, for example, runs ARM machine code. That's what it understands. Your desktop understands x86 machine code. That's what it runs. So in our managed code development model, what we do is we write our source code in C# or VB. We use the C# or VB compiler, compile it down to an intermediate form called Microsoft Intermediate Language, which is basically a set of pseudo instructions that is neither source nor assembly. And the .NET code generator takes care of translating the intermediate language to assembly instructions. There are a couple of ways in which .NET actually does it. I'll go into it in a minute. But this is essentially how code actually executes. It's this assembly code that actually executes on your device. So how does .NET actually generate code? So one form is called JIT compilation, standing for just-in-time compilation. This is what's commonly used everywhere, and it's also used in Windows Phone 7.5. So the idea here is, just before you execute a method, you compile that particular method down to assembly. So you're reading MSIL, and just before you know that you're going to call method X, you actually compile it down to assembly and run that assembly. So the advantage here is that you're only generating the code for the methods that you actually execute. The other advantages are, if, for example, one of your dependencies change, or if the framework is updated, it doesn't matter, because you're generating code just on the fly, just before execution. It'll all sort itself out. Easy deployment. You can xcopy deploy MSIL binaries and just JIT from them. Now, with all good things, there are bad things. So the problem with JIT compilation is that we are not going to reuse compiled code across app launches. So once you launch an app, you JIT a few methods, you exit, and you exit, and that code is thrown away. So the next time you launch an app, you have to do the same process again. You have to compile all the methods once more. The other disadvantage is startup. So JIT compilation is a cost. Every time you execute a method, you got to wait for some time before it can actually execute. Now, when you're talking about a few methods, it probably doesn't matter. When you're talking about thousands of methods, that can add up to a significant amount of time. Now, so on a desktop class machine, most likely, it's going to be a few tens of milliseconds, maybe 100 milliseconds, 200 milliseconds. You could say, yeah, that's fine. And one other point to keep in mind is the more optimized your code generator is, so the more stuff your compiler actually does in order to generate code that runs fast, the more time it's going to take for compiling. So .NET has another solution, Engine, which stands for Native Image Generation. This is commonly used by really large apps on the desktop, so which have thousands of methods that launch during startup, where startup takes 15 seconds if you do, just purely because of JIT compilation. So here, there is no JIT compilation. What we do is we generate the code, and we persist it on disk. So every time you launch the app, you have the code pre-generated, and you just launch that. So that's good in terms of startup. The disadvantages are deployment. So once you generate the code and persist on disk, if you have a dependency that got updated, or a framework DLL, say msco-lib gets updated, then you have to actually throw away the native code and restart. And of course, now your installs are a lot more complicated because you cannot just xcopy deploy them. There is an action that is needed on the device to make this work. So just to give a little more background on this problem, we were actually, a few years ago, we were in this world where processors were getting faster all the time. So we could say for most applications which aren't huge, JIT compilation was sufficient. 100 milliseconds here and there may not have mattered. And anyway, in a year or two, processors will be a lot faster. So that should take care of it automatically. And if you are a really huge application, you could do Engine. Yeah, it's going to take maybe, one of the things with Engine is you compile all your code because it doesn't know which code you're going to use. So you're going to compile everything. It might take, say, 5 to 10 minutes to basically engine all your apps. That's fine. It's a desktop class machine hooked onto power. That's all fine. But in today's world, we are actually, if you look at it, today's phones and devices are kind of the desktops of yesteryears. They are actually slower processors, less memory. So the things that I was talking about where JIT took hundreds or 200 milliseconds or something, right now will take few seconds, several seconds. So maybe 4 seconds, maybe 5 seconds. That's not going to be acceptable when you're actually launching an app. Most customers are going to launch your app, see that it doesn't launch in like a snap, like few seconds, and they're just going to walk away. Now, on the other hand, with Engine, the 5 to 10 minutes on a classic desktop that I mentioned, on a phone is probably going to be taking about an hour. So you don't want to be in the case where you had a framework update or a device update show up, and over the air, and you say, okay, let me do that now. And you go, do your thing and come back, and after an hour, you see that your battery is all drained because it took an hour to engine it, and compilation is a resource-intensive process. It's going to take up most of your CPU, and you don't want to deal with that. So the key takeaway is compiling on these devices is expensive. Whether you do it, just before execution, as in the case of JIT compilation, or if you do it at install time during using Engine. So what would be an ideal solution? We want fast startup. We cannot really give up on that. Customers need fast startup. But JIT cannot help us there. We need fast, easy deployment. We don't want to pay the installation costs. We want people's installation experience to also be smooth. And we want fast device updates. We don't want to wait. We don't want to basically do something for an hour or two, which is just burning up the CPU 100% of the time. So we'll go into why Engine actually needs basically something called cascaded recompilation. Why Engine is not ideal for device updates. So this is what cascaded recompilation means. If a dependency is updated, you basically have to update your own native code. So in this case, I just have a couple of apps, app1.exe, app2.exe, which are managed. App2.exe depends on a library, library.dll. And all of them depend on msco-lib.dll because that's the mother load of all managed code. So all lines lead to there. Now, cascaded recompilation is, if I update library.dll, you need to update app2.exe. So you need to throw away that native code and regenerate it. Now, in the extreme case, when mscorelib.dll is updated, which is what happens when there's a device update, you have to regenerate the whole world, basically. You have to regenerate native images for the whole world. That's pretty expensive. So how is it that we can resolve the problem? Well, one solution is we could say, yeah, libraries are stable, never updated. Yeah, well, that's not very pragmatic. We could say, okay, every time there is a new type, we can add it to a new DLL. Will work, but we'll probably end up with 1 billion DLLs every time we want to add a new type. The other option is we can statically link all the libraries into the app. Well, your app is going to be very bloated. It's going to take a long time to download. And not to speak about working set. Your app is going to consume because there's not going to be any sharing. So the root cause here is that base classes are fragile. And I'll talk about this in a little more detail. So for folks, I'm going to go a little more deeper now. So since this is a deep dive talk after all, but if folks want to tune out for the next few slides, that's fine. So an example of how this all works together. So there is a class base, with the 2 fields, int I and the string yes. This is how the object layout of that type looks. I can get my laser pointer to work. So the offset 0 points to something called the method table. The method table is nothing else, but it basically contains the pointers to where all the methods in the type lives. So in this case, you have a virtual method. A real method will, all the methods will be showing up in the method table. So that's pretty much it. So far, so good. And since we are talking about Windows Phone 8 here, 32-bit pointers, and that's why the offsets are 4 bytes each. Now, if there is a type derived that derives from base, let's say, and adds a new field to it, say int j. This is how it looks. And it has a method intfo. In this case, if you look at the type layout for app derived, the 0 pointer, 0x0 offset would actually point to the method table for the type derived, app derived, obviously. And you would have the 2 fields that are there in the base, and you will add another field which this type actually declares. So far, so good. Now, let's see what the assembly code for this particular method looks like. So int foo int a returns a plus j. So initially what happens is the value of this pointer is initialized into the R0 register. Since integer a is an input, that gets into the R1 register. Now, we know that we want to add a and j. So R1, since it's a, since it's an input, is already in the R1 register. So where does j live? So j basically lives in 0xc offset from this pointer. So that's what we do here. So we load the field j into R0. Basically, we add the offset of basically contained 0xc to this pointer in R0. So now we have the value of j in R0. And we basically add a and j and store it in R0, and then we return. This is just the equivalent of the x86 ret instruction. Good. So we can persist this code onto disk. Everything works. There's no JIT compilation needed. Now, the problem happens if you change the base class. So this happens, for example, when we update mscorelib.dll or any framework DLL that you have a dependency on. So here what we did is we introduced a new field, int k. So now int k is actually living in offset 0xc in the type layout for base. So you can see how this has actually messed up the type layout of the derived class. So if I looked at the code which we generated earlier, same code that I generated earlier, the problem here is now the derived class layout has to look like this, where 0xc now points to k, and j is now, since app derived derives from base class, it is actually now in hex 0x10. But the code that we have persisted is still pointing to 0xc because it thinks that's where j is. So your code is now invalid. It needs to be updated. So basically, this has to be 0x10. So that's why you basically have to throw your code away. Every time there's a framework device update, or a framework update, or a device update, or a dependent DLL gets updated, you have to throw that code away and regenerate your native code. In the JIT case, it doesn't matter because you're generating that code on the fly. So you're generating this code newly every time you run the app. So it's going to make sure Whatever you have right there is what you're going to use. So this is the code it'll generate. So when you JIT first before the framework update, it's going to generate the previous code. When you JIT compile after the framework update, it'll generate this code. But in the engine case, we have to regenerate this because we cannot, if we persist it, because this code is not going to, the earlier code was not going to work. So what we have to do here is regenerate. And when we regenerate, it'll basically, instead of 0xC, you change it to 0x10, and the world is hunky-dory. Now, I'm going to ask if anyone tuned out to come back. So the idea here is, if you looked at the code, there are some portions of the code that changed, but some portions of the code, or the majority of the code, was not actually affected at all. So if I looked at the code, just this one line changed. Everything else remained the same. So the simple, powerful idea here is that, can we compile to native code everything that is stable, and everything that is subject to change, let's actually keep them as placeholders that we can take care of later. That's essentially what we are doing when we do compile on the cloud. So we have a new language that we introduced called machine-dependent intermediate language, as opposed to just machine-independent intermediate language or intermediate language. Because it is ARM code that you're generating. So it is machine-dependent, but it has some placeholders in it. And at installation time, when you install an app, let's actually replace the MDIL, the placeholders, with actual native code, native instructions. So now, most of the compilation has been done, has been persisted, and it's just the linking step which takes care of those placeholders that needs to happen, which is not expensive. Now, when there is a device update, again, all what you have to do is to relink. You don't have to throw away the entire code. You just have to take the code, and the places where we added placeholders, we just replace that with updated native code. Now, you might ask, why did we need to go and invent a new language for this? Why couldn't we use something else? Now, the thing is, if you observe this carefully, not only was the instruction the one, not only, if you look at it, well, we had to change this one instruction. But if you look carefully, it's not even the instruction that needed changing. It's just this one offset that needed changing. Everything else, you could actually compile even that. It's just that we need to somehow find a way not to hard code the offset in. And that's pretty much what we do. So instead of hard coding an offset in, we just replace it with a field token. And at install time, what we do is we just call something, an MDI linker, which basically takes care of removing these field tokens and placing in the actual hard offsets based on what code exists. So when there is a device update, again, we just go through the app, the MDIL files, we replace these field tokens with hard offsets. That's it. And now you can see that we've kind of gotten the best of both worlds. We have our huge startup wins because every time you run, you're actually running native code. And the deployment and the installation hassles, where I told you had to wait for an hour before, during a framework device update, that's also kind of resolved because you only have to just look up certain parts in the code and just change them with offsets. You don't have to actually recompile. And so you can actually see you kind of get to have the cake and eat it too in some sense. So that's all fine. You might ask, but where's the cloud and the compile in the cloud coming from? So, we have this cool new technology, but for any technology to be successful, we want to make it easy to consume. Easy to consume from a developer's point of view, where it's transparent to the developer, and easy to use from the customer's point of view. So that's where the cloud comes in. So with your, when you actually write your C# code, you still do everything as you always did. You compile it, and you upload your MSIL apps to the App Store. In the App Store, what we actually do is we invoke the heavyweight MDIL compiler, which is an optimizing compiler. And since we are not running it anywhere on a device, or we can actually spend a lot more time generating higher code quality that runs fast, or code that runs fast. And we basically use the MDIL compiler to generate MDIL zaps. Now, when a user downloads an app, what they get is not the MSIL zap that you uploaded, but the MDIL zap is downloaded, and we generate native images out of it, and that's what we actually launch. User doesn't know anything because it just launches faster. Developer, no impact to you because you're still using the C# and MSIL development model. The heavy lifting happens in the cloud. Everything else is transparent. And the cool thing here is this is not just for Windows Phone 8 apps. Windows Phone 7 apps which run on Windows Phone 8 devices get this for free. So let me show you a small demo of this. No, we actually store the MDIL. So the question was basically, do you store the MDIL on the device, or do you have to re-download it every time there is a device update? The answer is we do store the MDIL on the device because it's just code, so we just link it. Sure, go ahead. Yes. Is it possible to generate MDIL in Visual Studio? Answer is yes, and that's what I'll demo right now. So we have, so what I'm going to do here is I'm just going to stop my earlier invocation. So what we wanted to do is we wanted to make sure that you have a very good debugging experience and at the same time give you the opportunity to generate and run native images as an end customer would, or generate MDIL and generate native images on the device. So by default, when you actually, let's say in this case, when I do F5, and I'm going to switch here for a second to, I'm just going to count the seconds. It's already 3, 4, 5, 6, 7, somewhere between 7 and 8 seconds it took to launch the app. Now, when you press F5, because we want to make sure that the code isn't optimizing away your methods and your variables, we actually JIT compile. So that's where we saw like about 5 to 8 seconds. This is on a debug flavor. But that's how it works by default. Now, when you actually do Control F5, we kind of assume, or Alt F1, profiling, for example, you want to run it as it would run on an end customer's device. So in that case, we actually generate MDIL, and that's what we install and run from. So let me just show you. Now, I'm just going to press Control F5, and I'll start counting once it starts. 1, 2, 3, 4, 5, 6. So between 5 and 6 seconds as opposed to about 8 seconds in the JITted case. So, and keep in mind this is a debug flavor, so all those caveats included. But you just saw that when I deployed MDIL, I didn't change the flavor or anything. I just did F5 versus Control F5. You can see the wins even when you're actually doing debugging. So that's how faster it is. Now,
you mentioned that the MDIL is an optimizing compiler.
Yep.
Are the optimizations that happen just now the same as what happened in the cloud with higher compute power?
Yeah. Yeah. So when you actually run, well, this is a debug flavor, but if you do it on a release flavor, it's pretty much the same. Yeah. So right now, the cloud and the basically the compiler that we have in the cloud right now is synchronized with what we have in Visual Studio for now. So basically, it's the same compiler that you're using. Now, one of the things that I want to point out is like, when on F5 I said that we fall back to, we basically JIT compile, and on Control F5 we do MDIL generation and run off the native images. Well, if you wanted to run MDIL and native images of F5, you still can do it. Or what you got to do is go to Tools, Options, and debugging, and you have to basically enable just my code, and there is something called suppress JIT optimizations. So you just take that off, and if you unselect this and select just my code, you basically will get MDIL even on an F5 scenario. But by default, we didn't do that because we kind of assume that when you're pressing F5, your intent is to debug and not to test the code as it ultimately will run. And for that, you have Control F5. Okay. I'll move back to my presentation. And again, all this is transparent. So as a developer, if I hadn't told you that this is what's happening under the hood, you would have just thought, well, there's some optimization that's happening and it's just making it faster. And that's how we want it to be. And as an end customer, they don't really care about what's happening under the hood here. They just see apps are launching faster. So now I'm going to be talking a little more about the compiler. So one of the things that I said is, we have an optimizing compiler. So there is kind of a Hobson's choice between, you can either, in the JIT compilation world, you can either optimize for compile time. So, you make the compiler dumb, you kind of make it slow, you kind of make it not generate that awesome code, or in which case, it'll do its JIT compilation really fast, but the code that is generated is not very fast. On the other hand, you could spend a lot more time JIT compiling, but what does that mean? You will generate faster code. That is, your code is going to run fast, but it's going to take a longer time to start. So with the model that I just described, with the compiler in the cloud, you actually have taken care of that choice because all heavy lifting is happening in the cloud. Customers never see it, so you can spend as much time as you want compiling. And at the same time, it's a native code that actually runs on the customer's device, so they get the startup wins as well. So .NET for Windows Phone 8, therefore, has a much more optimizing compiler than NetCF. So one of the things we did is we took the Box2D game engine, and we basically ran it as is on .NET for Windows Phone 8. And what we did is we took the same Box2D game engine and then hand optimized it to heck and beyond. Like, we basically did all sorts of inlining, loop unrolling, all the sorts of manual inlining. We did all that. And we thought, let's see how good the compilers stack up. So what you see here, and we ran that on NetCF. So basically, we hampered our .NET for Windows Phone 8 by running it completely unoptimized, whereas in the NetCF case, we actually ran it with all the optimizations that we could think of. You can see that even with that, .NET for Windows Phone 8 is actually performing faster. Higher is better in most of the scenarios than NetCF. So what does this mean to end developers? Well, you don't have to spend a whole lot of time doing manual inlining, loop unrolling. You don't have to spend any of those times manually optimizing your code. .NET for Windows Phone 8 will automatically generate more optimized code than NetCF. So the other thing that we get is an improved garbage collector. So once again, in the NetCF world, people used to do forced GCs because they wanted to make sure that the memory profile stayed within bounds, and made sure that because the NetCF GC didn't track lifetime intra method, that is within a method, it only tracked lifetimes across methods. People had to go through a lot of pain to make sure memory usage is low and apps are responsive. Again, with .NET for Windows Phone 8, we get significantly lower GC latencies because we have a 3-generational garbage collector. We have a multi-core allocator. So what this means is your allocation throughput is a lot faster now. You can allocate on every thread. And the .NET for Windows Phone 8 GC also provides you improved object lifetime tracking, which means that we actually track the lifetime not just inter-method, but also intra-method. So we can actually handle deletion of objects even when they are not used. Otherwise, in the NetCF case, if there's a variable within a method, we consider it live for the duration of the method. Now we just consider it live for the duration of method. It's actually live. So big wins here. Makes your app responsive. Now to summarize what I said here. So our goal has been to make it easier than ever to make you write great .NET apps, in particular .NET apps for Windows Phone 8. So we provided you with WinRT, which allows you to use native game engines, write hybrid apps. And you saw how seamless and integrated the whole shebang was. You didn't have to worry about pinvoke or any of the intra boundaries are already optimized. You can use code pretty much as is. Portable class libraries, again, offer you a very efficient means of writing cross-platform apps. Very important in today's world with the mushrooming of platforms. And not just the source. It also basically means you can compile it down to a binary and use it across platforms. Async programming, enough said. You saw how simple that model is. I went a little bit of a detail in the compiler in the cloud, improved startup dramatically, and automatically, transparently to both developers and users. And it works, as I said, like even Windows Phone, if you submitted a Windows Phone 7.5 app, that app automatically gets the benefits on Windows Phone 8 devices. You don't have to do anything. And our improved GC and code generator provides significant performance wins, among other things. we support multi-core, and all this adds up to a lot of performance wins. Your apps will start up snappily, will run fast, will have a very good memory profile. So before I call time on my deck, so these are some of the talks that I would have recommended. 3 of them are already done, but I'm assuming that you can get them on the web. The first one is at 12:45 today at the Nexus Normandy room. That's the one that I mentioned about portable class libraries that help you write cross-platform apps. And some more resources. So we have a .NET Team blog, and we love hearing from folks, so please ping back with us. Obviously, Windows Phone blog and Windows Phone Dev blog. We also have VS booths down here, which are manned by a few folks in the Common Language Runtime team will also be present there. And of course, please feel free to email me. I would love to hear from you. And with that, I'm going to call time on my deck and open it up for questions. Thank you. I'm going to request if you can please go to the microphone.
No. There we go. With the compile in the cloud, when we were actually running the application, are there still runtime optimizations that can take place from the JIT compiler, or is it completely statically compiled?
It is. So we use a mix, but for most purposes, you should assume it's completely statically compiled. There are certain cases where we do JIT compilation, but for the most part, it is statically compiled.
Is there a tool to view the MDIL?
Not publicly yet. We are not. That's not a document that we are exposing right now, format. So no.
Okay. And is there plans to bring this to the desktop CLR?
We are always thinking how we can improve the state of the art forward. But to that extent, we will be considering it. Yes, but.
You talked about how cool asynchronous processing is. Is there too much asynchronous processing? Like if I schedule too many tasks, all this context switching will probably kill me. So what power do I have to kind of control that?
Well, at the end of the day, what you want to do is you want to use it when it makes sense, because synchronous programming is still simpler. So lots of places, that's probably what you need. But I would say the most common places where you can use this to your benefit is if you're on a GUI thread and if you're doing, say, disk read, reading a file of something, common operations like that, web requests, anything that hits the web, it's something that's going to be, it's going to take a fairly long time, and you don't want it to be blocking other web requests. And if you have any long latency operations. So I think those are the places where I would put that in. Now, with respect to how much is too much, it kind of depends on, at some point, you're going to stop seeing the perf wins. So
to clarify, my concern really, you made it like really easy and cool to start the tasks. I don't need to think about it. Now what I see is junior developer comes in and starts, it's start here, start there. I have like 5 million items in the list, and each of them I want to load asynchronously.
Yeah.
And then next thing you know, you deploy, and then his module blows up, and you go in and like, oh my god. So it kind of makes sense to say I can schedule the task up to X, and then everything after X is suspended until first X are processed.
Yes, from a developer's perspective, we give you that control to make that determination. Because if you're looking at web requests, you can have several thousand web requests, right? At one point. So you have the control to do that effectively.
Okay. Thank you.
Yeah, you talked about the optimization for the WinRT wrappers.
Yes.
How does that stack against, say, pinbook on the C++ CLI approach?
So,
do you have any benchmarks that compare the various?
So I cannot give you an exact number, but what I can tell you is that's something we did focus on. So it should be pretty equivalent. You shouldn't notice any difference.
Is it better, or is it about the same?
I would say we have actually spent a lot of time optimizing that path, so I would be surprised if it isn't better.
I have two questions. Is there any plan to use a graphic chip on the phone within your native code compiler on the phone at some point? I mean, to do some kind of optimization that will see some loops that can benefit from using graphic chip.
Yeah, that's perhaps something we can consider in future.
Okay,
Yeah.
and the second question, if at sometime in future Windows Update will include update to the native code generator, does it mean that phone will need to recompile every application, not just relink it?
Come again?
If in future some Windows Update will bring a new version of the compiler, native code compiler.
Windows Update or Windows Phone Update, you mean?
Yeah, on Windows Phone
Update. Okay.
Does it mean that the phone will need to recompile every application? Because
no, because the thing is the compiler doesn't actually go into your phone because everything is pre-compiled, right? It's just the linker that comes to your phone.
I thought it's precompiled as into intermediate language, but it's still compiled into the processor instructions on the phone.
No, so what happens, what I said is, most of the instructions actually just do get compiled to assembly. Just a few placeholders are intermediate, are basically machine-dependent intermediate language.
So you're saying that MDIL is kind of a machine-level assembler. It's not kind of IL assembler that we see in MSIL.
Yeah.
Okay.
Yeah. It's basically you just have to replace. It's a linker, more like a linker, which replaces these instructions with actual assembly instructions.
So it contains ARM assembler language.
Yeah. Yeah.
Okay.
I have a question regarding you said it will compile to assembly what it can.
Yep.
If I have a UI library that makes extensive use of a portable class library, for example, is it recognizing that ability across both of those to compile most of it to the native, or do I need to combine those into a single binary?
No, it will recognize. Basically, if you have multiple modules and one of them is a portable class library, you do get the benefits for free. Thanks.
Two questions. One, when moving to the garbage collection mechanism, is going to be like a full GC with large object heap and background GC compaction?
So this is so the GC that we have in .NET for Windows Phone 8 is similar to the workstation GC, except that there is no concurrent or background GC.
Okay, but it's not actually workstation GC because you make allocation across multiple cores, like server GC.
Yeah. Well, we do make allocations across multiple cores. Yes.
Okay. And second question is about getting dumps. In case of an application crash or something, can we, as developers, get a dump file that can be analyzed after one?
After one?
Let's say post-mortem of the application.
So I think that's a question for the Windows Phone marketplace team. They have made some improvements to what kind of information that you get in terms of a crash. Mm-hmm. So that's probably, they are best suited to answer that question.
And on development machines, can I get a dump file on a development device? Let's say I have it on staging on a QA and I want to get some information which is not on the store yet.
So I am not sure of that. So let's take that offline.
Okay.
Thanks. I'll put you in touch with the right person. Yeah.
Just a quick question. At what stage the NGen compilation happens? When I upload my app to the cloud or when the user downloads it to a device?
So when you upload your app to the cloud, when we process it, when we ingest it and we say everything is good to go, when we respond to you, at that point the engine processing has already happened. So engine processing in terms of MDIL creation. Now when the user downloads it, there is still the small task which actually fills in the field tokens with actual hard-coded offsets. That happens on your phone. But most of the processing happens in the cloud.
Okay, thank you.
Sure.
Will the new compiler be ported to 7.8?
So will the new compiler be ported to the Windows Phone 7.8? No, it won't be. Yeah. All right. Thank you. Thank you for your time.